Welcome to this next lecture on fundamentals of acoustics. In the last few classes we derived the acoustic wave equation and discussed issues like steady state solutions, transients, and the type of excitations that the system could have, initial conditions, boundary conditions, and so forth. So I will continue along those lines. So as far as let us say boundary conditions are concerned, if I have to show them pictorially, let us say we have a duct or a pipe and at the end it is open to atmosphere, and so since we are looking at perturbation on mean, so the condition here means the pressure dash has to be 0, that is the acoustic pressure has to be 0, that is the boundary condition over here. Let us say this is driven by a piston oscillating back and forth with a velocity u0 e to the power j omega t. Okay. So this is called the pressure release. The other one is we have, let us say again a pipe, it is driven on one end by an oscillating piston, but this end now is rigidly closed, it is called rigid walled. Or the velocity v tilde at L comma t is 0, which in terms of pressure ends up as del P del N equal to 0. Okay. So which means what, we have a gradient of pressure, okay, and we take a dot of N such that it is the normal, that is equal to 0. Okay. Because gradient of pressure is directly proportional to velocity, okay, which is a vector. Okay. So we take the component of the velocity in a particular direction such that it is normal to some surface, and so it reflects on the gradient, it is a directional derivative now on the pressure. Okay. So next is we have this situation where we again have a duct, let us say, and driven on one end by a piston, but here it is now neither pressure nor velocity. I have a situation where I have a mass loaded with a spring. Okay. So now this is an end impedance. So here this is like saying the pressure divided by the velocity, okay, into let us say the cross section area to make it a force, that is the end impedance ZML tilde, which in this case would be, J times m omega minus the spring constant by omega. Okay. Here also we can put a v dot n, actually v dot n. Okay. If we consider velocity there to be a vector, I mean we are looking at very simple geometry, so velocity which direction is known, so we are taking it as a scalar, but if we consider velocity to be a vector, then we dot it with n, which is normal to that surface, then it becomes a scalar, okay, and on the numerator we have S into P to make it a force, and we have ZML, okay. Alternatively, we take P tilde, or let us say again V tilde over N, then this is Z tilde ML over S, which is now called the specific acoustic impedance, okay. So this will be J over S, S is doubling up, okay. So this S is a spring, let me call it SP, and this is the cross section area. So M omega minus SP by omega, okay. So this is now specific acoustic impedance, which has units of pressure over velocity, and it has all the same implications as mechanical, except that it's at a point, okay, because pressure is at a point in space and velocity, particle velocity is the same point in space. So it's a point property, it's a point property, whereas the Z mechanical actually involves the area also, and therefore it's kind of an integrated over some area. So later we will say what is called the radiation impedance of a surface, okay, which we will integrate over an area, and look at P over V ds. So this will again have mechanical impedance units, okay. So leave this idea for now, we will talk about it when it comes. So we have acoustic impedance, which is pressure over velocity, and given by Z tilde A at a point in space. Now just as I have done with strings and rods, I just like to quickly show you that the same expressions are available. It's a bit of a repetition, but the whole course is about sound, so in 1D sound at least I need to show you, okay. So we will take a case of a driven semi-infinite duct. Driven semi-infinite duct, okay. And so the configuration is, I have a pipe which, or a duct, okay, duct or a pipe, use alternatively. This goes off to infinity and starts at x equal to 0, and here it is driven by a piston driven. Piston oscillates at u0 e to the power j omega t velocity, okay. Now this is governed by the 1D wave equation, del 2 p tilde del x square is equal to 1 over c square del 2 p tilde by del t square. So this is the 1D wave equation. For acoustics, it has the same form as the string, it has the same form as the rod, okay. That is why we did the string and the rod and looked at all implications. Now again p tilde here, x comma t, because it is semi infinite, it will be given by e to the power of minus j k x e to the power of j omega t only, okay, because the pipe is semi infinite, it goes off to infinity, so cannot have a reflection. So b tilde is 0 plus b tilde part is 0, okay. So there is only one unknown, one unknown, A tilde. Okay. So how do you find this unknown? At the left end and our Euler equation, our friend Euler equation, always remember. Okay, what is that? Del P tilde by del x is equal to minus rho 0 del V tilde by del t. Okay. Now we are talking harmonic dependence everywhere. Okay. So if I do this on the left side, I get minus jk, and this is okay. This is the Euler equation. Let me not pollute it right here. Okay. So we are going to use this. You are going to use this. Okay, to relate pressure to velocity at x equal to 0, and x equal to 0, piston velocity is u0 e to the power j omega t. That is the idea. So how do we do this? We say del p tilde by del x at x equal to 0, that is equal to minus j k a tilde e to the power minus j k x evaluated at x equal to 0, that is 1 e to the power j omega t. Let me keep it. That is equal to minus rho 0 del v tilde del t, and v tilde has the same time dependence. So the derivative brings me a j omega, and I have v tilde. Okay, and within v tilde there is e j omega t. So I will always play this game of e to the power j omega t, keeping it and not keeping it with awareness. Okay, because it's a bit cumbersome keeping track. So now this e to the power j omega t goes away, and I have v tilde, and from here the negative sign goes, from here the j goes. Okay, so I have k a tilde given by rho 0 omega, and at x equal to 0 the velocity is u0. Okay, that was the condition. So k is omega by c, so a tilde is rho 0 c omega u0. No, omega is also gone. Rho 0 c u0. So the one unknown we have has been found. So my solution now p x comma t is rho 0 c u0 e to the power of, let me say, j omega t minus kx. Pressure over particle velocity is commonly known as specific acoustic impedance. That is the main acoustic impedance we will be looking at for a while. So I will address it as acoustic impedance, but actually it is specific acoustic impedance. Towards the end we will see another impedance that will actually be known as acoustic impedance. So pressure over particle velocity is specific acoustic impedance. Okay. So let us now compute. We want to compute the impedance. This time we will compute specific acoustic impedance. Acoustic impedance, okay, which is P tilde over, let us say, V tilde seen from the driver. So how do you get the V tilde? Now we already know del P del x, del P tilde by del x is equal to minus j omega rho V tilde. Okay, I'm just going the long route because let me not take the long route. Let me do it straight away. So, the pressure at x equal to 0 is rho 0 c u 0 e to the power j omega t, and velocity at x equal to 0 is u 0 e to the power j omega t. This time it is simple. So, the specific acoustic impedance is rho 0 c. Okay. In case of the rod, you had got rho 0 c s as the mechanical impedance. So, you can see that between mechanical impedance and acoustic impedance there is a cross section area difference, nothing else. Now, this is real, so we know what real means, and in particular this number rho 0 c, if you get, is called the characteristic impedance of a medium. Impedance of a medium. This product has a name. So, the acoustic impedance is the characteristic impedance in this case. Okay. And because it is an infinite pipe, there are no resonances. Pipe, no resonance, etc., etc. Okay. And power from the driver moves away to infinity along the pipe. Okay. All those implications are there. Okay. So, this is pressure at a point and velocity at that point. It is a point property, that is important, point property. Later on, as I said we will look at radiation impedance, which is a surface property or integrated over a surface. We will see that later. Okay. So, that was the first case. Okay. Just to show you that everything is same once we have this form. Okay. So, one more case we look at is a driven. So, driven meaning piston driven, finite, okay, rigid ended duct or pipe. So, I have a pipe of length L, let us say, and here is x equal to 0, is driven by a piston, and here is rigid ended, meaning the velocity dotted with n is 0, okay, or del p del n is 0 at x equal to L. Okay. Now, we have seen enough expressions, so I will make it a little quick here. So, what I will do, I will take this expression p x comma t a tilde e to the power of minus j k x plus r L tilde e to the power of minus 2 j k L e to the power of j k x e to the power of j omega t. Okay. So, I am measuring or adding waves at a certain location x. This is my origin. This is at a location x equal to x. The ingoing wave is a tilde e to the power of minus j k x. Okay. Then, because excitation piston is persistently exciting, it is not stopped. So, this wave goes, okay, a certain length x L minus x, it goes L minus x, and it comes back another L minus x. So, what will it travel do? A tilde e to the power of minus j k x e to the power of minus j k L minus x e to the power of minus j k L minus x. Okay. If we add all that up, a tilde e to the power of minus j k x plus L minus x plus L minus x. So this x goes. So I get a tilde e to the power of minus 2jkl e to the power of jkx. Okay, that's what I have. A tilde e to the power minus 2jkl e to the power jkx. All this is just travel. This part is a phase change due to travel. Phase change seen by the wave a tilde, which was a tilde at x equal to 0 and which was a tilde e to the power of minus jkx at x equal to x. It is this much after it has travelled a full pipe length and come back to the location x from the left. Now this boundary will do something to it, that has to be put in, that is RL. Okay. In this case it is a rigid ended pipe, so it is rigid ended, and so velocity is 0, or del P by del N is 0. Okay. So P will be a maximum in that case. Okay, P will be a maxima in that case. So my R tilde L will be plus 1 because pressure gets reinforced. Okay, at the end velocities have gone to 0. So incoming velocity and outgoing velocity are opposed, and so the incoming pressure and outgoing pressure will be at the maximum. They will add in phase. Okay. So I'll tell you kind of so you have a pressure that is going, let's say it hits it positive at this is the point it hits at x equal to L. Okay. So it will have a velocity going that way. Okay. Because why? Because this is a plane wave. We are looking at a plane wave. In plane wave, if the pressure is a tilde, the particle velocity is just rho 0 c. Okay. So if I have a maximum pressure here, the velocity will go along with it and it is towards the right with just a ratio. Now I want the suppose this gets reflected. Suppose this is reflected, okay, as a positive pressure traveling this way, okay, and that let's say is B tilde. Then the velocity due to that will be leftward, so it is minus B tilde by rho 0 c. Okay. So now if A tilde and B tilde are equal, then my velocity goes to 0. This is velocity goes to 0. That means what? An in phase pressure has to be generated by the end traveling leftward, and therefore what happens? A positive pressure at the end and an in phase pressure traveling leftward, they two add up. So you have a pressure maxima. You have a pressure maxima where you have a velocity minima. Okay, and that's why my RL tilde in this case is plus 1. So if we go with that, I have P tilde x comma t is equal to A tilde e to the power of minus jkx plus 1 e to the power of minus 2jkl e to the power of jkx e to the power of j omega t. Okay, and the particle velocity x comma t is equal to a tilde e to the power of minus j k x by rho 0 c minus e to the power of minus 2 j k l e to the power j k x by rho 0 c e to the power of j omega t. Okay. So now we equate the at u at x equal to 0 comma t is given by a tilde, okay, by rho 0 c 1 minus e to the power of minus 2 j k l e to the power of j omega t. Okay, and that happens to be u0 e to the power of j omega t. Okay, so let me take this to the next page. Okay, so now from here e to the power j omega t goes, and a tilde is given by u0 rho 0 c divided by 1 minus e to the power of minus 2 j k l. Okay, then what is my pressure expression? Pressure at x comma t is equal to u0 rho 0 c 1 minus e to the power minus 2 j k l e to the power of minus j k x plus e to the power of minus 2 j k l e to the power of j k x e to the power of j omega t. Okay, so now u0 rho 0 c I take e to the power of minus 2 j k l common, I get e to the power j k l minus e to the power minus j k l. In the numerator I take e to the power of minus j k l common here, I get e to the power of j k l minus x plus e to the power of minus j k l minus x e to the power of j omega t. This goes and I get u0 rho 0 c by, this is 2j sine kl and this is 2 cos kl minus x e to the power of j omega t. So that this 2 goes away and I get pressure given by minus j rho 0 c u0 cos kl minus x by sine kl e to the power of j omega t. Okay, I would like to compute acoustic impedance at x equal to 0, but I already know my particle velocity u at x equal to 0 comma t is u0 e to the power of j omega t. Okay, so if I take pressure at x equal to 0 and particle velocity at x equal to 0, I get minus j rho 0 c u 0 cos kl by sin kl e to the power of j omega t by u 0 e to the power j omega t. This goes minus j rho 0 c cot kl. Very similar expression to what we got for strings and rods. So this exercise is to show that for a 1D acoustics case, it is the same as the string case and the rod. Okay. So let me just do one more thing. If we have the traditional expression a tilde e to the power of minus jkx plus b tilde e to the power of jkx and ej omega t, then in order to find the particle velocity, I will use the Euler equation. I will get a tilde minus jk e to the power of minus jkx plus b tilde jk e to the power of jkx into e to the power of j omega t. Let me take this. Copy, paste. Okay. Then that is equal to minus j omega rho velocity. I am using velocity sometimes u tilde, sometimes v tilde, it is okay. Okay. And there is the ej omega t, as I said, we have this issue all the time. Okay. So if I take out this, okay, the u tilde x, okay, u tilde x, that means without the harmonic part, is going to be equal to 1 by minus j omega rho, let us say rho 0, minus j k a tilde e to the power of minus j k x plus j k b tilde e to the power of j k x. Okay. This j goes, this j goes, this j goes. K is omega by c, k is omega by c. So I have omega, omega goes away. So what I have, I take this minus inside, I have a tilde by rho 0 c e to the power of minus j k x minus b tilde by rho 0 c e to the power of j k x. That is my u tilde x. If I bring in the temporal thing, this is the temporal behavior. So with what I want to illustrate, with a tilde e to the power of minus j k x pressure going rightward, particle velocity is a tilde by rho 0 c e to the power of minus j k x. With b tilde e to the power of minus j k x pressure going leftward, particle velocity is minus b tilde by rho 0 c. Okay. So this is for a plane wave, not elsewhere, plane. Okay. We will see some more about 1D acoustics in the coming lectures. I will close this lecture here. Thank you.